All right, hi there. Let's get started. So first things first, if you do have any questions, just put them into the chat. I have a second screen over here, so I can check them out every now and then, and I can answer them directly if they're there. Apart from that, yeah, nice that I can be here. And the next like 40 minutes will be more of a architectural or a generic talk, not about a concrete system or anything like that. How data stores have changed because of the evolution of cloud services. And we'll just cover like what has changed and also what kind of impact you have to expect from that. Because it's not just that the systems themselves have changed, but also how you work with them. So what is the impact for cloud providers, for your business, for developers, and what's the reason for all of this? So hi there, I'm Alex. I'm coming from the databases and distributed systems space, spent almost a decade at Elastic. That's also why I'm a huge JVM fan. Been working remote for almost a decade now, and currently at Firebolt, which is a distributed cloud data warehouse. So if we think about the cloud and like the move of applications in the last decade, I think like the most common strategy is sort of lift and shift, which basically means you take your existing applications and move them into the cloud, be it by containerizing them, by repackaging them, be it by moving whole instances over there. But that's the most common strategy, like move things over and then optimize. And for databases, the strategy often was very similar, right? Like you didn't really think about using cloud functionality for your database. You had your existing data store, moved that one over and used it within any cloud provider. And of course, the cloud provider always wants you to consume more cloud services over time. And for data stores in the cloud, this usually meant you had looked around like, what is the cloud provider offering? And like, of course, there's always minor modifications, even if it's a hosted Postgre version or anything like that, because the system needs to adapt to the control plane of the cloud provider. And of course, sometimes you have a version lock-in because you're always dependent on what the cloud provider offers, what the cloud provider offers as an upgrade or updating strategy. So there's some sort of lock-in if you want. And that can be often circumvented by using not the cloud provider's software as a service data store, but the database provider. Many providers of databases nowadays basically offer the same functionality by allowing you to run the database, and you can often pick the version. There's some way you can't, but most of the time the version lock-in is much smaller than if you go with one of the big cloud providers. And of course, you can still host this yourself in your own Kubernetes cluster if you want. So that option is there as well. Most of the time you try not to do it, not because it's necessarily cheaper on a per hour base, but you try to circumvent things like the upgrade complexity or the maintenance work. You don't want to upgrade systems or kernels just for your data store if all you want to do is having an interface to execute some SQL. So let's take a look at the evolution of architectures of data stores. So it all started with a single system. Think of your Postgres server where you had like one node handling writes and reads in parallel, writing to the local disk. There was no coordination required from a networking perspective. Everything could be done local. It was easy to handle transactions because you knew immediately which kind of operations were in flight. And of course, you had the big single point of failure. Like if this system went down, there was no availability. And the scaling strategy was pretty much a money strategy. Like unless you found a fancy algorithm to optimize on, you always had to scale up, meaning you had to buy bigger hardware in order to have a faster system. Yeah, Postgres is one example, but there are many others of the older data stores. And then the next step was to decouple reads and writes. Like the common architecture here is the sort of leader-follower architecture, where you basically have one system accepting all the writes, and then one fans those writes over to the other systems, and they accept reads. And this is how you split between those. You still have a single point of failure because there's only one system accepting writes. And also some of the complexity moves over to the client, right? You need to know about your system architecture suddenly because there are several systems accepting reads, and you also want to make sure you don't overload a single of those systems. So again, there's some complexity involved, but all in all, it's pretty manageable. The scaling strategy now is split. you can add more nodes if you need to sustain more reads, but you still have this scale-up strategy for writes because there's only a single system. Again, Postgres or MySQL or things on top of that, like Vitess, are probably a good example. And then the next step in the architecture was sharding and replication. So you kept more than a single copy of data, and you also had a cluster. So you had a distributed system that constantly talks to each other. And the more you have copies of your data in a cluster, like in the leader-follower architecture, the more read scalability you have. But you can also split the data across the system now. So you have 10 nodes, each of them taking a tenth of the data, means you can write 10 times more throughput than on a single system. And you don't have a single point of failure in the best case in such a distributed system, which of course comes at the price of coordination, right? Like the system needs to figure out which system is up, which system is down. If a system goes down, how do I move my data around to provide all the consistency guarantees that have been configured? But it also offers zero downtime upgrades, like just doing a rolling upgrade of a system, for example. And the scaling strategy is usually scale out. You grow the performance and the size of your cluster by adding more of the same nodes in many cases. But it comes at a price, like complexity, more coordination, more maintenance, because like you need to figure out if something is down at 3 a.m., like what is going on in the distributed system. And also you sometimes duplicate writes, right? Like so far, we had only a single system writing the data. Now we have several, and you have to cater for that. You have to plan more CPUs to write your data, more I/O, more disk. And that can be expensive, right? Because if you want to make sure your data is like 3 times in your cluster, you probably write the data 3 times, and that just needs to be accounted for as well when you calculate your costs. And Elasticsearch is one of those systems which now is already 12 years old, which support this kind of sharding and replication mechanisms. One problem with this approach is reads and writes are not really decoupled. So the moment you have a system where lots of reads are happening, writes are probably slower and vice versa. And this is not really what you want. And the common workaround of this is that you have a cluster of systems, and only the most beefy nodes are basically ones accepting writes and also reads. And so you solve this by sort of creating a tiering within your distributed system, like hot, warm, or cold nodes, or however this is named. And that's a common strategy to solve this. And then the sort of more recent trend, at the end, it's not really recent because we've seen that before in the terms of an event bus, for example, were streaming platforms. And often nowadays, not always, but often, like streaming systems are just treated as a buffer. So you can send a lot of data there, and the system behind that doesn't need to be able to cope with all the data coming in at once. It just needs to be able to keep writing data. And if you're lagging a little bit behind, it doesn't matter because the streaming platform is a buffer. And that's a good strategy because it decouples writes. And there's one sort of disadvantage that because you add another system to your architecture that's explicitly meant as a buffer, that you increase the cycle time from the generation of an event until it's hitting your storage, right? And that's not necessarily a problem or an issue. It's just a fact of how this architecture works. And of course, like system, think of Kafka with the Zookeeper setup, it increases operational complexity at this stage. And that's something that you need to be aware of, but it's often a price that's happily paid. So if you would like to sort of write a modern data store, what's the goal? Well, the first thing we would like to do is decouple reads and writes so we can scale independently. We also would like to write data only once because it's economically feasible. And if you write only once, it's pretty obvious that this writing data needs to be shared among all the readers. You would like to keep coordination to a minimum, and you can replace like this hot, warm, cold architecture probably just with tasks. I would like to have 10 writers and 3 readers. And if they are not needed, I would like to scale them down. If using like cloud infrastructure, you may get things like cross-region replication for free. But the uttermost and foremost reason you would like to do this is always cost reduction. Like the pressure on cost is usually the biggest thing. And this brings us to the companies which are most interested in cost reduction. And that's the hyperscalers, right? Like AWS, Azure, GCP, like the really big cloud providers, they've done like major advancement in the last 10 years, and they will keep doing it, right? And just taking a look at the object storage, like S3, GCS, things like that. Like they've gotten so much better, right? They have now strict rules and durability that after you write something, you can read it immediately. So the semantics change, speed got much faster. So with this object storage is advancing, maybe a modern data store doesn't need the replication on an application basis, like we saw in the leader and follower architecture or on what Elasticsearch is doing. And this gets us a lot more closer to the goal of writing data only once. And of course, we also saw significant price drops over the last decade, right? Like I think storing a terabyte is now something like $20 a month, and depending on where you do it, it's even cheaper. But reading the data is also costly. But still, like prices have only known one direction over the years. And we also have to say, like those hyperscalers, they rule the data world, right? They have the biggest incentive to drive down the cost of services. Like if you have a service and you can shut it down just for an hour of the day because it's not used, like in terms of a hyperscaler with this insane infrastructure, this is a huge incentive. And that's also the incentive to scale down to zero, right? Really, it's all about cost savings. And like the hyperscalers have always been a major driver for changing how data stores operated. And they're usually also a little bit ahead. You can see this in how companies are founded by former Google, Microsoft, or Facebook employees, for example, that they are just a couple of years ahead, and then everything else slowly flows into other data stores. So scale to zero is kind of a term to have an application that really doesn't need any CPU. So you just need storage to have the application or the container image somewhere. And this all started with the scaling to zero runtime environments, being AWS Lambda or Google Cloud Run. Like, as you can see, AWS Lambda is 8 years old by now. And that was the first thing, right? Like code is only, or a system is only needed when the code really is executed. But apart from that, it's lying dormant, and just the code is somewhere that it's ready to be loaded, but there's no compute instance required. And for code, this is relatively easy, but for databases, this is much more complex because they are more stateful. But even in 2018, so already 4 years ago, I think AWS Aurora was the first system to introduce this, and we've seen a few others since then. And what is marketed as a big change is just a drive-by effect of trying to scale to zero from the hyperscaler perspective, and that is the pay-per-use, what you do with AWS Lambda or AWS Aurora. And in order to make this work for data store, you basically have to be able to shut down without losing data. So you cannot store data on a compute instance. You have to store the data somewhere else. Startup has to be quick. So in case you shut down, you also want to come back as quick as possible. And this implies that storage and compute are split because you don't want to lose any data when your compute instance goes down. So if we want to share the storage among all instances, we also would like to read the data with as many readers in parallel as possible. So that should be free. And if we need to write data, we obviously have to have some sort of coordination, no matter if that's by locking a file or claiming to lock a file, or if that's by another coordinator process. If this is the object storage like S3, then there's one thing pretty clear, and that is it's way slower than local storage, right? The local SSD will always be a lot faster. So the question is always, can we deal with this from a data store perspective? And that also means you need to become object storage smart. That means things like a full table scan, which will probably be still okay on an SSD, may become really slow on a slower storage like S3. Also, each object storage has different access patterns. So in some storages, you can access ranges of a file instead of the whole file. And if you know what ranges to retrieve, because you have stored this information elsewhere, you can reduce the amount of bytes that get sent back and forth. And of course, whenever you optimize something about how to retrieve your data, you will not just mean less CPU or just require less I/O. You will also lower the bill of your system. And that's a really interesting part because it gives you a completely different incentive to make a data store compatible with any object storage. And sometimes you would like to assign exact costs to queries and index. I don't think that's really possible if you have a caching layer in between. So that's also the reason why all the serverless offerings pretty much have a fixed price for a certain amount of operations. The other side is compute. You can now split by tasks once you've written the data to an object store. You can just shut down if there's no activity. And of course, you automatically create some sort of distributed system because compute and the object storage are split. Also, you can have tasks like cleaning up or merging or vacuuming on a SQL database. They just can be another compute instance, right? You don't have to tie them to indexing or querying. So that allows you to do some sort of cleanup tasks happily in the background while the system is running. And whenever you have a local storage like an SSD, this is always only a cache. This is never, ever like a storage medium to store and persist data. It's always just to speed queries up or to speed some tasks up, but that's it. And this comes with the trade-off of an increased latency. So like think of this when you have your SQL database and you write a single row. There's usually not only the data written in whatever data structure you have, something like a B tree, but there's also a write-ahead log, which is just really fast at writing data. And this write-ahead log is just much slower with an object storage. So it's by definition batch friendlier. Like the bigger you write a file, the faster it is usually on the object storages. And it's not really suitable for millisecond latency. It's just a thing to be aware of when you create a data store there. And like this is a nice blog post. So or an excerpt from blog post about the event storage system used at Datadog. And they said like this increased latency is fine. And also the increased latency when running queries, because we don't have super fast access to disk, when we can eliminate like crazy tail latencies, right? And that's an interesting trade-off that they were willing to do because they kind of said, I'm happy to have a stable system that's a little slower and more predictable than have a really fast system that can also be occasionally really, really slow and so is less predictable. And that's the kind of interesting trade-off that they chose to do, which makes complete sense in combination with something like an object storage. And if we take a look at the different storages nowadays that split between storage and compute, we basically see from a category, there's not this one system that is doing this. It's happening all over the place, right? We have analytics in here. We have data warehouses in here, regular distributed SQL databases, or like an extension for Postgres, Neon. That's an interesting one, like Firebolt, the company I work for, ClickHouse in the analytics space. So like this is not happening in isolation. This is really happening across all the data stores out there. And it will continue to happen from my perspective. The thing is, this trend isn't new. Like the first data warehouse that probably did this was Google BigQuery in 2012. So it's quite a few years back, where they really started to split between storage and compute in there. And you could just pick what you would like to execute. Again, we were not talking about like regular SQL database for application development, but rather like the data warehouse-like functionality, I would say. And one of the things to keep in mind is, and this is why you won't see this happening for all the data stores out there, is that this is complex. So a couple of weeks ago, Elasticsearch or Elastic published a blog post about their plans about going stateless, where they explicitly mentioned they also would like to separate compute from storage. And one of the reasons was to simplify cluster topology. And you could also see from a reasoning why they did this is that a couple of really like big IT companies started writing their own search engines that were basically really tailored to their use case, to their stack. Like CalDB is a Lucene-based logging system using Kafka, Zookeeper S3. NLT Search is also, I think, a search engine running in a Kubernetes environment. So instead of a sort of general on-purpose system like Elasticsearch that's also running on-premise, like this is very defined system boundary that they can make use of. And with these boundaries, it's much cheaper to run. And Elasticsearch doesn't want to miss out here, obviously. But the one thing that they figured out and that should be obvious is like if you have an existing system, like retrofitting the split between storage and compute is a lot of work, right? Like this blog post states that just the proof of concept was a multi-month thing. So the whole experimental phase and going live will probably take even longer, and fleshing out issues and bugs. But that's what it is, right? An existing system and moving this over to splitting storage and compute is just a lot of work. And if you ask yourself why they are doing it, it's obvious. You still have this tough competitiveness from other companies, especially from the hyperscalers, in terms of pricing, right? Like writing data twice is an expensive endeavor. And if you can prevent it, you can run the same workload, probably much, much cheaper on any Elasticsearch-based system. So it's clear why it's done. And the trend of data explosion is just continuing, right? So you still want to provide like economically feasible storage system that can store right now terabytes of data, but soon probably petabytes of data, and still be able to query this in a short time frame. And that comes at the same position, like if you need to query more data, you probably also need to reduce resource consumption so that you can do this with the same systems. And there are a couple of other nice features. If you keep your data in the object storage, you can do funny things like point-in-time recovery. You can go back in time and see how your data looked like. Like, please give me the data from yesterday, and then like import this in another system. So just having this available might be interesting for a couple of use cases. Or you can fork your data at a certain point and then go from there with your new live data if you want to play around with it. And one thing that I think will come in the future is that the split between storage and compute, if you have an on-premise system offered, may be a differentiator in the software as a service offering without being available on the on-premise system, right? So you have sort of different implementations of backends or interfaces there, depending on if you're running in the cloud or if you're running on-prem. So all of this has downsides. And one not so obvious one are the hyperscalers. So they are a threat to open source or to VC-backed open source, depending on how you see it. But of course, if a hyperscaler decides to host an open source software on their infrastructure as software as a service, no one is forced to contribute back, right? That's the thing with open source. But the hyperscalers obviously have an advantage there because they own the infrastructure, they know the infrastructure, they can easily integrate it into the control plane. So the playing field is not leveled, right? There's an implicit advantage for the hyperscaler just because they can use their infrastructure probably in a better way. And that makes it really, really hard for other open source software projects. And also there's often the discussion of the big ones not properly contributing back, just taking what is there and using it, which is fine by the license. But it's a major discussion happening. And that led to a lot of relicensing across the industry, right? Like there was Mongo with the SSPL, Elastic, Confluent, Greylock, Grafana, Redis, Cockroach, Couchbase. They have a specific license which kind of flips to open source after a certain amount in time. And it also led to a very, very well-known fork with OpenSearch. And now we basically have two communities with Elasticsearch and OpenSearch, one driven by AWS, one driven by Elastic, and the other companies which prefer running Elasticsearch as a service, they're hugely on OpenSearch, but like getting the users over there is really, really tough and really, really hard. So that's basically an issue for everyone involved if you want. And if you want to know more, there's an interesting blog post also about this whole communication from the open source initiative about licensing called Righteous Expedient Wrong, which is a good read, which was written when Elastic changed their license. And like there's a few trends you can see based on this. And one is that the monetization of open source software kind of moves over to software as a service nowadays because you would like to keep this intellectual property without anyone profiting from that, right? And there's also change from open source to open code. Like Elasticsearch still is like completely visible on GitHub. It just has this tiny license edition, like don't run it as a service without paying us. But the way of development hasn't changed. And this may lead to like less open source in the future or partial open source, or like that the control plane is not open source, but just the tool itself. So like this makes things harder for others to probably run software. And we'll end up with more black box systems. And also we end up with different compatibility guarantees, right? Back then it was like the source is the same of a system that we're running, but nowadays there's the we just say SQL as a query language is enough. The rest is done in the background. We know a lot of systems which are Postgres compatible because they know that they then can simply use a lot of tooling. Or the wire protocol is the same. This has been done, I think, by AWS, where they had a MongoDB compatible wire protocol. So they claimed that this is compatible and you can use the service. But then you have to figure out as a user, by running the same tests on MongoDB versus that system, if it's really compatible or if it's just a claim. So the work is kind of offloaded to the user, and you never really know, even if the communication protocols look similar. And also development becomes more complex. So the data stores of this generation, they don't run on all cloud providers, right? And this means that this is first an existential threat to the smaller cloud providers. Think DigitalOcean, Scaleway, Vultr, OVH, you name it. But it also means that you as a user have to pick one of the bigger cloud providers or a smaller cloud provider next to it in order to make sure that you have fast access to your systems. And of course, like, not only they will not run on cloud providers, they will also not run locally. And that means things like testing are always over the internet. This fast feedback loop that you have locally from running a unit test needs to be made sure that this is still possible by probably mocking it away, whatever. Offline development will not work, but I think that trend is going like away anyway. And of course, you don't have pre-production systems because you only have this one live system. And you don't have cheap CI runs. I think that's a major difference to me, right? If you have an on-premise software like Elasticsearch, you can just fire it up within, I don't know, test containers or manual or whatever, run it within CI and see if everything works. You just need the resources, but you don't need to pay for that in addition. And that's a major difference if you run like such a software as a service system, that you probably need to also calculate in your daily runs that CI suddenly has a price attached to it that may be saved by running smaller instances because that one is running elsewhere, but it needs to be taken into account. Debugging is another thing that basically turns a little bit more into a black box, right? Things like IOPS or bandwidth from the remote storage, they may be burstable, which means they have a short amount of time where it's really fast and then it slows down. And you need to know a lot more details about the instances that are actually used in the background to also know these kind of things, right? Same for the network speed. That is also probably burstable because it needs to be shared among several tenants. And that brings us to a much harder part about like performance stability and predictability. Again, that can usually be solved with buying bigger instances, but it's just something to be aware of when running into performance issues. Is it your application? Is it the backend? And like how and where to measure it. I think it's all about observability in this context, and it just needs to be there. When we before we go with the summary, I just want to reiterate on the architecture, and that again, not everything is as easy as described earlier, right? Like in your best case, you have this kind of architecture where you have a dedicated writer that writes into the object storage. And then you also have this dedicated reader, and the reader reads the data, you execute a search or SQL query, whatever, the data is read and returned. And if everything is really running well, you have several readers and you have several writers. But this is obviously only half the truth, right? I haven't even talked about transactions and linearizability, serializability, like how does a writer know what the reader has available to read and what the reader is allowed to read because it's within a transaction or not. So you can solve all of those things, but they are just at another level of complexity and they need to be kept in mind. And the question is always, do I need some component helping with coordination or not, even within this kind of systems? And let's take a look at this really simple use case, append only. And the question is always like, when is a write done? Like when have I written so much data that the reader is ready to happily consume it? Like this is the question. And it's tough, right? Like we have batch data, maybe we're writing hundreds of megabytes at once before like our write is done. And we always need to make sure like this, there shouldn't be any reads of that partially written data. And also moving files around it's not an atomic operation in the object storage. So we probably need to have a mechanism of notifying readers of new data. Maybe that's kind of a direct network message. Maybe that's writing a certain file in the object storage where the reader knows, okay, now I can read the other file. Depends, but still you have to have some sort of notification mechanism. Updates and deletes are again a different beast, right? Because usually you don't do any in-place updates. Usually what you do is you mark something as deleted, which is somewhere in your data, and then you create a new entry for it. Again, we have to notify readers of this new data because we want to make sure that the most recent data is read. And what you don't want to do is that the same data is read twice. So once the old version, once the new version. And if you use SSDs as a local cache, you also have to take care of invalidation, right? This is especially important in this context because the one thing you don't want to do is delivering stale data to your customers or query systems. Same applies for cleaning up and vacuuming. So if you want to remove unused data, you first have to figure out like what is unused data. How can I be sure that there's no reader reading this data anymore, right? On a Linux system with a local SSD, you could delete a file and it would just be kept open with the inode until the file is really closed. So it would be just floating around and the system could read it. It's completely different, like when it's on an object storage, you don't have this notion of an inode in there. So you have to figure out at another position what's the most or the state where the reader is basically on. And if you would like to do that because you have like a compaction going on, that's a common mechanism to remove the data that is marked as deleted, and also to have bigger segments so that the compression is better, things like that. You just have to figure out, can I delete this data or do I have to keep it around and delete it later maybe, despite creating a newer segments? So again, there are ways around that, but it's not completely coordination free. And yeah, if we don't have this notion of inodes, as I already mentioned. And that brings us to some coordination that needs to happen. And maybe if you're smart, you can solve a lot of coordination by writing the data right into the object storage, and that by continuously reading the object storage, that may help, or by using other cloud native systems like a queue, like everyone subscribes to a certain topic and gets all the news, so you get your coordinator for free from there. But yeah, you need to have this one component that talks, right? Like when is data ready to be queried? That's something the writer needs to tell. And also obviously the other side, that someone needs to retrieve this data, or also when can I trigger something like merging and vacuum? Is it a cron job? Is it if I've amassed so much data, or if there's so many documents marked as deleted that I work on this? So all of this needs to be taken into account for coordinating instance. And the other part is, if this is a process, like, do I need to persist the state of this process as well in case it crashes, right? And if I do I write it to the object storage? Like, what happens if this coordinator dies? What happens if I have two coordinators accidentally started? So all of this complexity of distributed systems, it doesn't go away. And yeah, of course, like you can always embed this into another role, but the complexity just stays there. And that brings us to our summary here. I think the first thing, despite all the problems from a development perspective, is that we will see more and more of those data stores operating only in the cloud, operating only on top of the big hyperscalers, and making heavy use of the existing infrastructure. I don't see this trend going back, because the way they operate, the way they can reduce costs for really a lot of data is nothing that I do see on the commodity systems there. And also, like, only the cloud storages will really be able to store this amount of data, right? If I would like to store a couple dozen terabytes now, it's going to be really hard on my local systems, or buying a system in the rack. And the recent trends with hardware being, or with a chip crisis and hardware being really hard to buy, it basically plays a lot into the hyperscalers as well, because they have those systems available, whereas buying them and waiting for them nowadays is really complex. I think the whole topic about like resource consumption for CI and development is sort of an not unsolved problem. You can just spin up more instances, but it's often overlooked. And we have to be really careful when calculating how much money we will save, that this is not only about the one operating or the one system running and operating, but it's also about the costs for development. And that's something that can easily add up as well. Imagine having a team of like several dozen engineers. They all need their either own instances or a share for running one, plus CI. Probably CI is even more expensive if you have a really fast CI or big CI infrastructure. And yeah, I'm not really worried about offline development in general, like that everything needs to run on premise. But I'm still worried about everything needs to run fast locally if I'm writing my code, including integration tests. So probably a system like test containers or an infrastructure like test containers to run things locally will be faster, but doesn't need to be. And yeah, I think with the cloud IDEs on the rise, like all of our development will move into the cloud anyway, so that maybe the system running in the cloud is near to where my code is already, so that I don't need to be worried about any slowness there. We can just be able to run tests in the same environment, in the same availability zone, and be good with it. All right, so we have a little bit of time of questions, should you have them. You can also like put things in the chat. The QR code, which I will show in another second, is the link to the presentation. And if you're interested to learn more, like I have one major and big recommendation, and that is the CMO database talks at the top here. So the Carnegie Mellon University has a complete like course on database optimization, query planning, things like that. So really starting from the ground and going into detail over time. But they also have a series of database talks where the founders of like modern and recent databases talk about their architecture and their implementation details and their decisions. And that is extremely interesting because you learn a lot. It's basically a YouTube channel. Just search for CMU database and you get the channel immediately. And every half a year, they have like 20 talks from different databases from the main developers. And it's super, super interesting. I can just highly recommend it. If you need books, I think Designing Data-Intensive Applications has been out for a couple of years. There's a kind of getting started lightweight book called Understanding Distributed Systems that is also really good. There's something called the Firebolt Cloud Data Warehouse white paper that is good. And as a final thing, like I just want to repeat, like nothing of this is really super, super new, right? Like the whole thing has been existing in the infrastructure of the big cloud providers for some time, similar to what Kubernetes is nowadays, right? Like the infrastructure is Google Borg probably has run there for many, many years before this got public. And it's the exact same here. And with that said, I'm going to take a look if there are any questions now. And apart from that, thanks a lot for listening. Enjoy the rest of the conference. And if you have any questions, feel free to ping me on any of the social medias or drop me an email and ask your question. And if you make a photo or screenshot of this one here, you will be able to take a look at the presentation. Thank you so much.